Hey guys, so welcome once again. So today we're going to talk about lift, and we have two ways of explaining lift, which is the Bernoulli's principle or using the Newton's third law of motion. And we know that these two ways of explaining lift have, of course, their limitations. So today we're going to discuss that, and we're going to look at how we can explain lift in a way that is a bit more wholesome. So first we're going to look into the Newton's third law of motion, which says that for any force there's an equal and opposite reaction force. So that one can be used to explain lift based in a way that the air which is going to be interacting with the aerofoil is going to be deflected downwards, and that will cause an equal and opposite reaction, which will cause the lift. We can also look into the Bernoulli's principle, which tells us that the air flowing above the aerofoil will have a high velocity, hence low pressure, and the one flowing below the wing will have a low velocity, hence high pressure. So this pressure difference will cause the general lift in an aerofoil. That is by the explanation given by Bernoulli's principle. So the limitations of these explanations is that with Bernoulli's principle, we are not told why, or it doesn't explain to us why there is a difference in air velocity. In Newton's third law of motion, we're not told why an aerofoil can produce lift with zero angle of attack. Angle of attack is the angle at which the aerofoil interacts with the relative airflow. It has to make a certain angle for it to produce lift. So that is one drawback of its, or one way we cannot account for by the explanation of Newton's third law of motion. So today I'm going to explain to you how we can explain lift using both ways, and it still is wholesomely right, or a way that we can justify both explanations. So here we go. So what we need to know is that for lift to be produced by an aerofoil, there has to be a deflection of the airflow. What I mean is that the airflow has to be deflected downwards, meaning the airflow will have to change its trajectory or its direction. That one will of course cause an equal and opposite reaction, which is Newton's third law of motion. But what we're going to solve about Newton's third law of motion is the reason as to why an aerofoil can produce lift at zero angle of attack. So let's get to the point now. In Bernoulli's principle, what we are not told is that how is the airflow above the wing getting faster than the one below the wing. So what I want us to look into here is that for the wing to produce lift, air must be deflected downwards. And if we look into an aerofoil, we can see that it's usually mostly curved, somewhat pointing downwards, having that the upper camber will have a longer distance than the lower camber. So what this means is that in that camber there's a slight angle of attack. If we tend to look at this wing, the angle of attack we will measure by drawing a straight line from the stagnation point at the leading edge to the trailing edge. This line will help us find the angle of attack by means of finding the angle between that line and the line found by the relative airflow. So what we notice is that in as much as a wing might appear to be lying straight relative to the airflow, most of the time we are made to look at it by considering the baseline or the undersection of the wing. But what we really are supposed to be looking at while finding the angle of attack is the line that cuts straight from the stagnation point to the trailing edge. So what we notice is if we cut this line this way, then the air flowing above the wing will have less resistance because it has less obstacles in its path. The one flowing beneath the wing right after the stagnation point has more obstacles to get through. So that will generally lower its speed and make it move slower, while the one above the wing will obviously move faster. If we try and put a straight or flat plane on the path of an airflow, we will notice that the airflow above that plane and the airflow below the plane will have equal speed or equal velocity. So this means that it's the obstacles that we get into the path of that airflow that will make the difference in the airspeed. So that way we can justify Bernoulli's principle by saying that it is the obstacles that come at the path of the airflow that cause the difference in velocities. So in Newton's third law of motion, we can explain lift by saying that the air is deflected because the wing is angled, so it bounces off the air flows downwards, and of course it doesn't produce lift at zero angle of attack. So that is because at zero angle of attack no air is being deflected. And even if we were to put a cambered aerofoil, if we would subject a cambered aerofoil to an airflow and see at zero angle of attack, meaning the line cutting from the stagnation point to the trailing edge being parallel to the relative airflow, it will still produce lift. So this is the reason why. If we look at it from this point of view, we will notice that the airflow above the wing its trajectory is being changed gradually, and it's being changed in a progressive manner, while the airflow, which is going to be moving beneath the wing, will have a vigorous change in path, which will not be easy for the air flowing under that wing, while the one flowing above will have its trajectory changed gradually. So what we notice with this is that the one above the wing will have a smoother flow, or it will have an easier flow, while the one below the wing will have a lot of turbulence. This will generally cause difference in velocity, which will cause difference in air pressure, which will cause lift. So that way we can justify Bernoulli's principle, or we can give the reason as to why an aerofoil with a cambered aerofoil, or one with a longer upper camber and a shorter lower camber, can produce lift at zero angle of attack. So generally, a way we can define lift, or a way we can explain lift, is that an aerofoil produces lift based on its ability to push down on air.